decision making, right? So the whole uh, set of issues, right? If you really want to close this loop in a general way, there are a lot of challenges that I have to deal with. And definitely these are at the modeling level, at the system level, at the data analytics level, right? That across the spectrum, there are a huge number of challenges that that one would have to deal with. So what I'm going to do now is I'm going to talk about a couple of scenarios, um, just to give you an idea of some of the things that recently where we have tried to use this concept. Now we, I mean broadly, and then I'll try to dig into one or two challenges that we have tried to address, and then end with a broader set of research issues that hopefully other people can take up and work on. Right. So Radu mentioned the COVID-19 HPC consortium. Right. So what is this? Right. So this is March of 2020. We just understanding the scale of this pandemic and the fact that everything was going to lock down, life was being disrupted, and a bunch of people just got together and say, no matter what you do now, computing and data is going to play a huge role. Right. So how do we put together resources nationally, globally, and make them available to the research community to, in a really expedient way, right? Of course, time scales was something we're still grappling with, but as quickly as possible, right? And I'm not exaggerating here. Within a week, we were able to put together resources across 4 cloud providers, IBM, Google, Amazon, and Microsoft, all the DOE lab, Department of Energy, US labs, these are the big machines they have, all the National Science Foundation resources, university resources, put them together, and within a week and a half, there were people running on it. Right? This was fundamental research on how do I understand the virus, its propagation. It was logistics, right? How do I make sure that my ventilation is right? How do I make sure that, what is the propagation of supply chain, or how do I route supplies, or how do I manage logistics, like how do I board an airplane, right? So this kind of research, and they would come in, say, I want to do this. Within a day or two, they had access to the resources and go on, and then we kept on making it faster, right? But the process was that as quickly as possible, data and compute should be accessible to everybody. And the impact of it was tremendous, right? We had a lot of fundamental research, but we had a lot of applied research, right? For example, one case I always like to highlight is that there was a shortage of ventilators, right? This was, I think, June of 2020, right? There was a big shortage in the US of ventilators. And they were looking at techniques, what can we do? And one technique was, how do I split a ventilator across multiple patients, right? And there was this researcher in Duke University, Amanda Randalls, right? And she came up with a model and a design to do this. And she went to the Food and Drug Administration and said, I'd like to approve this for early use. And they say, oh, you have to run all these tests, right? And so within that weekend, all of, Microsoft just put together a huge bunch of resources along with NSF resources. And we were able to run those simulations, and on Monday, they had approval to use that, right? So that's sort of the paradigm that we were trying to use here, right? This is the aggregate statistics we have currently. Well, this suddenly is now winding down, so that's the other part of this kind of thing is when the crisis is passed or the other resources, you need to wind down. So now this is winding down, but we had 43 consortium members, including 7 international members, like Japan, Australia, the UK, Sweden, Switzerland, South Korea, right, and a few others. So we had international members that part of that. An aggregate of 600 petaflops was there. There were over 120 projects. It's a bit old. So you can see, how you can bring computing together and data together and respond, right? And here the response was in a day, but you can see scenarios where the response could be minutes or seconds or hours, right, depending on what you're trying to do. Here's another. Oh, I'm going to digress once more. And what we're doing in the US is to learn from that and to create something that's more strategic, right? We did this in an ad hoc way. As I said, it was done in a week, right, without any prior agreements, without any prior structures set up, right? So we are in sort of adapting on the fly. How do I do single sign-on? How do I integrate and federate these resources? How do I move the data? We are discovering solutions on the fly. The idea is to step back and to think about this strategically. Can we set up a national strategic computing reserve, right? Just like the petroleum reserve and the other national reserves that a country has, we need a computing reserve. And the idea there is when there's a national emergency, whether it's a weather emergency, hurricanes, fires, pandemics, cyber attack, right? Can we harness all these resources collectively and make them accessible to first responders, to researchers, to the logistics people, so they can use it immediately? There's a blueprint out here that was put together on what the issues are and how one would do it, right? It's early days, but this is just a partnership between government, academia, and industry to start thinking about this strategically. And I can think about this as a national global computing reserve, right? Where everybody starts bringing these resources. And one thing we know, no matter what the crisis is, computing data is going to play a huge role in responding to it, in coming up, right? And I can't think of any such crisis where computing would not, or data would not play a role in coming up with a strategy, right? And so having something like this can be tremendously useful. Here's another use case, and this is more academic. That was something that we actually deployed and we used, and we showed the benefit, but also what did not work and why we need to think about this strategically from design rather than after the fact, right? So this is more for research that we were looking at. This was some work that was published in the AAAI conference, in 2020, and it was judged as an outstanding paper for social impact. But the idea here was, how do I provide an extra few minutes or few tenths of minutes before an earthquake hits by creating an early warning system that does a few things. One is that it can aggregate different types of sensors to be able to detect the earthquake waves earlier, right? So you have the P waves, which are the surface waves, which are easier to detect. And then you have the subsurface waves, or the S waves, which really cause the damage. But they move a little more slowly. And so if you can detect the P waves early, you can start making preparations, whether evacuation or something like that, right? The problem is the P waves disrupt the seismometers, right? And so they undercount the P waves, right? So the process of measuring them, because of disruption, and especially when they're high magnitude high magnitude earthquakes, the P waves can be very disruptive, right? And so your measurements are always underestimated when you're doing them early. However, GPSs do a great job in being able to measure P waves, right? Especially high magnitude P waves. So if I could combine GPS, which are quite pervasive, along with the strategically placed seismometers, I can detect these much earlier. The second part of it is, can I, rather than aggregating all the data in one location, a cloud, can I spread it out? So I'm doing it incrementally using resources at the edge, in transit, in the network, and at the cloud. I can save a lot of time, right? And so what this says is, can I come up with algorithms and models that can gather the data, both seismic data as well as GPS data, aggregate them incrementally, right, using these learning methods that we built in this work, and then bring them together, and then be able to detect these P waves much earlier, right? And so this is really looking at a few different things. Can I integrate these resources? Can I come up with algorithms that are more decentralized? And can I combine sensors in different ways? And it demonstrated that if I did that, I can actually be much more effective in providing earthquake warnings earlier, right? And the impact of that is just tremendous because now you have an extra few minutes to get people out of the way to start taking contingency plans and things like that, right? And so these are just two examples, but one can think of other examples, right? Here are a few more that we have looked at, but I'm sure all of you here can think about scenarios where you could do these things in a way, right? I could identify events, I can accelerate decision making, and I can trigger a response, right? And so this is sort of the idea that it's trying to do, right? We have all these technologies, we have these ideas, we have the algorithms, we have the systems. Can we actually put them together in a way that provides me with some constraints on time, provides me with some guarantees on quality, so I can actually do timely decision making, right? And rather than building specialized systems to do that, can I aggregate systems that we already have deployed right now, right? So if I look at this and try to think about some of the requirements, and this is not exhaustive, right? What are the different requirements? Clearly, I need to do some sort of a timely, maybe real time is strong for all the applications, right? Some of them need it, but some timely delivery of information, right? So that I can use it, right? And that means I need to be able to not only gather, but also process it in a timely manner, right? So I can basically use computing, what I need, when I need it, to be able to process it and be able to gather the insights, the knowledge I need from the data to be able to make these decisions. I need to be able to describe the workflows to do this, and rather than our regular workflows, right? These are more data driven because this data flow and the control flow of the workflow depends on the data, right? It depends on what I'm seeing in the data, right? So it's really a very dynamic data-driven workflow. Clearly, some amount of automation, autonomics is important to make the trade-offs. Do I collect more data, or do I just use the data I have because I have to make a decision and I don't have time to either gather the data or to or to or to make the decision and process it and make the decision in time, right? So what are the cost benefit trade-offs that I have to make on the fly, right? Yes, I can get more data, it's higher quality, my decision improve, but if it's delayed, it's not useful, right? So how do I make those trade-offs in a timely way, right? So how do I build in autonomics into the thinking of this entire process? And clearly one can think about a lot more of these, and then the system level challenges, privacy, um, um, fairness, security. So there are clearly typical distributed system challenges, but I think these are unique to this data-driven, time-constrained way of thinking about these things, right? So let me switch a little bit, right? Given this motivation, this idea of computing in the continuum, right? And again, something I've already talked about before. Clearly, right? We have a quickly evolving computing landscape, right? And here are just three things that we talk about, but you can still broaden this with the new technologies and deployments that are coming on, right? So we have the core data centers that are integral to our infrastructure, and clearly they have tremendous capacity, right? On demand, all the capacity you can get, but they are expensive, sorry, inexpensive, right? And fine, but they're far from the data, right? And just going back to the presentation example, right? There was no way I could have gotten my presentation onto the cloud in time to give this talk, right? But that's a trivial example, but you get the idea, right? And data access tends to be expensive, right? They're not designed to let you quickly and cheaply take your data out. That's more of a policy issue, and that might change, but typically that is always a concern, right? And then we're talking about fog edge, right, which are closer to data, give you lower latencies. They're clearly limited in their capacity, storage and compute, and can be expensive, relatively speaking. And then finally, with our network elements becoming more and more powerful with this whole concept of DTNs, or data transfer nodes, that are these beefed off network appliances that provide you tremendous computing and data capability. Now you have this intermediate computing that you can deploy along the data path that provides you with some trade-offs in cost and benefit and availability, right? So being able to create really a continuum, a spectrum of capabilities both for processing across it, right? So it's not just everything has to be done in the cloud, but I have many different options with different design trade-offs that I can use in an optimal way to be able to uh, do my processing, to do my data analytics, do my decision making, right? And I can try to be able to orchestrate them in an effective way so they can meet my needs. Right? And so that's basically the simple idea around the computing in the continuum, right? Is basically how do I, in a data aware manner, context aware manner, use this entire spectrum of resources I have, cloud, edge, in transit, fog, all of them, weave them together into a computing environment that meets my need. And to be able to use it effectively, such as deciding what to use, when to move the data and when to process, how much to process, right? I can use the edge and process, but I may not be able to run my highest resolution algorithm there. Now, is it more important to get the highest resolution analytics, or is it more important to get the analytics in a second, right? And I have to make that trade-off, and I might have to do that at runtime. Maybe if I see my P wave amplitude is really high, I want to make something quickly, right? If it's emerging, maybe it's worth making a more a deliberate decision by doing more analytics. Right? So there's so many factors, but you need an infrastructure and a framework where I can make these trade-offs in a timely manner, right? And so as this graphic or cartoon shows, right, how do we really balance this spectrum that we have from the edge, a lot of data, very little compute, other constraints, energy, for instance, to the other end where we have a lot of compute, but high latencies and far away from the data. There are clearly other people thinking about it. Again, I'm quite sure this is an old and incomplete list, but clearly, you know, there are other people who are thinking about this a lot. There are other people who are working on this idea under different names or the same name of looking at the continuum. I'm going to highlight one project here, and again, with acknowledgement to Ilkay, because she's going to talk, she might have already spoken about it. Right, this is the SAGE project that Ilkay is part of, and it's led by Pete Beckman, and it's trying to prototype, deploy an infrastructure that embodies this concept of a continuum. It is trying to be able to build devices, right, that are at the edge, that are powerful, that are programmable, that can be scalable and integrated, but also connect them with the core, with clouds, with HPC, with large-scale computing. So you're creating this continuum, right? So you can create them at the edge fog level. You can put them right on the sensors, and you can integrate them with the core, right? And I'll talk a little bit about this, right? So this sort of cartoon tries to sort of give the whole concept of it, right? So it's building this programmable infrastructure where I can deploy my AI and get it to run across the entire spectrum, right? So you can think about sensors, large facilities. These are shared instruments, large telescopes, sensor arrays, experimental facilities, tokamaks, right? You can think about large facilities as well as actuators, right? And so you can deploy the computing there. So it creates the hardware platform, but also the software platform where I can use technologies such as containers to be able to deploy my codes there and integrate them as part of my workflow, right? And then it also then ties in with clouds and data centers and HPC, right? So that I can really complete this spectrum, right? It's just a tremendous project that's really creating a test bed where I can start looking at this holistically, right? It's just an exciting thing. I'm just going to give you one example here. So that is what one of the SAGE node looks like at the edge. They have a bunch of sensors, but they also have connectivity, right? Both wireless and wired. They have processing power, right? So there are some GPUs in there. There's storage. There's right? So that you can do non-trivial amount of computing there, right? But then it connects as part of a national network of nodes to the cloud, so that now you can gather data, you can discover data all over the place, and start stitching it together, right? And so in this case, they're looking at monitoring one of these controlled burns, and I'm not going to try to explain myself right now because again, Okay, I probably talked about it. Um, but right, and so here's another example, right? Can I use this to be able to uh, uh, create AI at the edge for wildfire detection? And the reason I wanted to put this up is, right, this platform would it's they sort of create this app store of models that you can then deploy as black boxes onto the edge device and integrate them into your workflow, right? And so these are different tools. Like this is one of the tools developed by a student, right? And it can be deployed into this framework, and you can use that to weave your data pipeline or workflow and integrate it into an application. And so given this background, right, what we've been thinking about is how do I, given that I have this concept of a continuum and a platform like Sage on which I can build on, how do I start programming applications, right? And so we've been trying to think about this for some time right? We started working with Sage recently, but for the last few years, we've been thinking about what would such an environment look like? If this is part of the applications that I want to build, what are the different pieces, right? And we have sort of looking at it at least three different levels, right? So this is a project. The first one is Comet Cloud, which is a a project that I've been working on for some time. And the simple concept there is, how can I integrate resources together, federate resources, and use them collectively, right? How do I deploy applications on a network or a federation of different resources, right? And so we've been using it for different type of scenarios. We did it in the peer-to-peer. We do use it for grids, and again, we're just using the same infrastructure here for cloud edge continuum integration, right? The top one, VDC, is a project which is about data services, right? How do I build science-aware data services for data discovery, for data access, for data sharing, right? For example, some recent work here is looking at, what would a recommender system look like for scientific data, right? So we know what recommender systems are. They tell us which shoes to buy and which shirt to buy all the time, right? Can I also do that for scientific data, right? And the motivation there was that an average instrument has hundreds, sorry, I take that back, 100,000 data products coming out of it. And often finding the data is very, very hard. And that's why I know the instrument. If I am trying to use data from another instrument, right, I may not even know what data they have because they're so domain specific. So the model here is, can I start building recommendation systems to be able to get the data that's most meaningful to me based on certain parameters that I'm interested in, right? Based on maybe the science. If I looked at pressure, maybe I need to get this density or salinity because I need to, there's a data product that everybody uses that uses pressure and salinity, right? And so, well, here's something that could be recommended to me. So we've been trying to build that. And so there are other such data services there. But what I'm going to focus on here is this piece here, our Pulsar, which is a programming system, right? A library that allows me to build applications that are data driven. And I should acknowledge here one of my postdocs, Danielle Tomet, who's been key to this and has contributed a lot to this work. So what is our Pulsar? It is a programming system that allows me to build these data-driven pipelines, right? And the idea is that I can specify what to do when a certain data comes, where to do it, right? And when to do it, right? So I can basically start defining that when I receive a data, I can define simple policies that say, if you see this data, do this at the edge at this time, right? And so I can start building simple data-driven pipelines using that, right? So it provides you with programming support and system management to be able to really compose different services and deploy them at runtime based on the data that I get, right? So basically, it has these decoupled interactions in the sense that interactions are based on the content of the data and are decoupled in space and time, right? They're just completely asynchronous, and uh, what you program are these reactive behaviors, and that basically says that if I see this, and it could be a system event, it could be a data event, when I see this event, do something, right? And there are other tools that allow me to do this as well, and so this is just based on this model. Rules are simple, if then else rules, right? I think the key contribution is also is in the flexible way that I can define data patterns and in the scalable way that I can execute it, right? So again, it's allowing me to define interesting data patterns based on some understood taxonomy, right? I'm able to define these data patterns, and once those data patterns occur, I can then uh, deploy certain workflows in certain in certain locations, cloud and edge, right? So the different type of reactions that can be done based on this. So there's a few different components here, and I'll try to explain this whole thing in one slide. So it's a bit of a complex slide, but there are a few different concepts out here, and there are a bunch of papers that I can point you to that go into how does it work, how does it compare to other systems in terms of performance, in terms of scalability, in terms of expressibility, right? So the basic idea is a message, and message is a simple thing. It has a profile, which is a set of keywords that are defined in terms of some ontology that everybody agrees on, right? And it then has also action, and the action could be simple thing as store this data. It could be send a message, send a notification, or it could be more complex, which says run a workflow. And there are some other things that I will not talk about. For example, location might talk about security aspects in terms of privacy aspects, or it might talk about locality in terms of a physical space, right? So there are a few other extensions out here, right? And then you have profiles. So every data item has a profile. Every action has a profile, and it's again nothing but a set of keywords, right? And then you have rules, which are if then else rules, which say that if I see this profile, or if I see this pattern in a profile, then do something. And the do something could be simple things as trigger execution of a workflow. It could be a simple thing as send a message or notification, or trigger another rule, right? So it could be a chain thing that you can create with that. And then you have this notion of associative matching, right? Which basically what it does is matches these profiles, and once if the profiles match, it then triggers these actions to take place, right? For example, C1 sends a message that gets received by the into this cloud or all pulsar system. C2 then says that notify me if this data comes in. There's a match, and the notification gets out, right? Like a pub-sub system, right? But it's a little more powerful than a pub-sub system. The key innovation out here is how this is implemented in a scalable way. And the way this is done is using some concepts that became very, very popular in the early 2000s called, this in peer-to-peer networks called distributed hash tables, right? Based on consistent hashing, right? So being able to build a DHT that allows me to really scale the matching in an effective way. And the other innovation is, so a DHT consists of a storage, but an index, right, that I hash into. And so the other innovation here is how do I create the index? And that index is derived directly from my application space. And again, I can get into how you do that, but what that allows me to do is that the only thing that two communicating entities have to know is the set of keywords, right? After that, it automatically is able to do this kind of a pub-sub or a associative matching in a scalable way. And again, there are papers on the performance and things and the guarantees of performance around that, right? But that's sort of the big concept out here. What I'm going to focus out here is how do we use it, right? In Sage, right? So in Sage, we have deployed it on top of the platform, right? And we can get different sensors, right? So we can connect to any of the sensors in the Sage network, and then I can define my rules. And these could be on individual data values. They can also be on windows, right? For example, I'm not interested in the number of cars coming in this camera. What I'm interested in is what rate are the cars density changing. That's probably more interesting to me than just the number exactly, right? So I can start defining operations on window and react to that. And then you have a bunch of different rule matching, which says if I get this, send me a notification, trigger another rule, run this workflow somewhere, make some system adjustments. For example, go to low power mode or increase, come out of low power mode, right? So I can do a whole bunch of different actions based on this simple paradigm, right? And again, I think there's a URL somewhere in this presentation which can take you to where this code is and tutorials and things like that. Okay, and this right here, right? So this has been implemented. It's built on a few different technologies. It's been deployed and you can download it and use it, right? And it's evolving. Again, it's research software, but we are continuously hardening it. And as following our idea with translation is we want to make it accessible as broadly as possible, mainly so that we can get feedback and see whether this makes sense. We also compare it to other things like Kafka, but Mosquito and all the other pieces of software that are out there right now, right? And see what the benefits are as well as what the relative costs are. Okay. So what I'm going to do is just give you one set of results. How am I doing for time? Pardon? 10 minutes more. Okay. All right. So I'm close to the end. All right. So just a few results, right? So I just wanted to show you that this, that it works. I mean, it is evolving, and we are continuously optimizing it. But we did some evaluation here. We looked at different policies. Run my computation only on the cloud. Run it on the edge. Run it between the edge and the cloud. Do it in a dynamic way where you're constantly adjusting where to run it based on some policy. And then we had a simple deadline scenario which says that do the best you can and give me a result within a certain deadline, right? We had a constant environment, but we also looked at simulated variable environments. For example, what if my data size was changing? What if my bandwidth was changing? What if my CPU capacity was changing? How do I adapt to that, right? And so I'm going to quickly go through a few set of results, right? Okay, and then we had some other results. So this was deployed on Grift 1000 in France, and we ran experiments there. We emulated an edge plus cloud environment using that and different system parameters, and then we looked at the normal performance metrics, time to completion, compute time, data transfer time, data quality, acceptance rate, right? This is an interesting scenario that we used. This was a part of a collaboration with a colleague of mine when we were working around the Hurricane Sandy in New Jersey, right? This was a few years back. It was quite a severe event, and I remember personally we didn't have power for a week, but it was a lot of damage. And one of my colleagues, what he did was he had this van that was outfitted with LiDAR, and he went around the disaster area, imaging the whole thing, right? And since then, we've been working on how can we use this kind of imaging data to be able to make urgent decisions about critical infrastructure, right? And the idea is that we need to figure out which roads which bridges, which buildings can I use? And what they do is they have imaged this before and image it on the fly after the event, and they can quickly triage it. They can say, this is fine, this one is bad, and this one we need more time to figure out, right? And so in a time of emergency, when you are trying to get people out or get supplies in, being able to figure out which roads and bridges I can use is so critical, right? And so what we were working on was, how can I make this decision on either the drones that they use or in this van itself, so that they can quickly react to this scenario, right? And so we had deployed it on their drones, right? But for this experiment, we took the same data set because we had a more controlled environment where you could run these multiple experiments. We emulated that scenario on Grid 5000. Okay, and so that's really what you're saying. You're looking at the data set, and you're running this edge detection algorithm on these images and trying to follow this decision tree on the slide there that allows you to make a decision what to do. So here are some results. I hope you can see them, right? So this is the constant environment. Basically, what you're seeing out here on the x-axis is the time to completion, and the y-axis is the batches of images, right? So you're getting these batches of images coming in from the sensors, and we're trying to make a decision on those images and process them on the fly. And you can see how, I mean, a lot of this is intuitive, what you would expect to see. On top, you can see that the data transfer time to the cloud just kills you. If I'm doing at the edge, you can see the compute time is a lot longer, and there's no data transfer time. If I'm able to balance the two, I can start getting better time. The scale on the y-axis is not the same, but the continuum is better. And then if I can do things more adaptively, I can make more effective decisions to be able to do a few different adaptations. What do I do at the edge? What do I at the cloud? And there's also this approximation, right? In a batch, I can process all the images, and I can downsample the images and process a few of them to meet a deadline. And there I have to balance the error versus the time saved and see what's reliable. And in the deadline and the dynamic, I do this kind of approximation as well. This one looks at a more dynamic scenario. In this case, I'm varying the data size of the that I'm getting from the sensor as per that bell curve up there, right? And you can see that a lot of these track this, but you can also see that the dynamic adapts to this much better as opposed to the more static approaches. And again, the deadline is able to make the adaptations, right, to maintain quality, but downsample the images. All the top four are processing all the images in a batch. The bottom one is only processing the images that it can, given the deadline that you have, right? And then the third one is looking at a lot of variability, and here the results are mixed. Sometimes we do well, sometimes we don't. But what we're doing here is we are varying the data size, the bandwidth, and the CPU capacity using different distributions, and we're trying to see, right, what happens. And then here you can see that, for example, in case of the dynamic and the edge only, we're able to do better because we can more effectively use the resources there. In terms of the deadline, we do moderately well. We have to violate the deadline a few times, but we, maintain reasonable quality of the decision making. But on the whole, we are able to do well. Again, this is a work in progress, and we are continuing to understand how can we again add more knobs at the algorithmic level, but also understand better how we can make these decisions. Actually, there's some recent work that Daniel has done, which starts building models, right, on this, so you can predict some of these behaviors and be able to make more effective decisions on what adaptations to make, right? Again, I can point you to the paper that goes into some more of that. So here is some more work that's going on. This was just one piece of it. There is other pieces that we've been working on. For example, how do you do decision making in a smart factory? How do you do better modeling of the operator placement in this continuum, and so on, right? So again, just to give you an idea that this is part of some broader work. So with that, let me conclude, right? I know I'm running against time, right? So clearly, there is compute and data everywhere, right? And we need to be able to rethink how we build our applications to better leverage this pervasiveness of compute and data to be able to make decisions in a reasonable and timely manner with sufficient accuracy so I can actually, uh, impact situations. And when there are crises, when there are urgent situations, that becomes even more important. And one way to do this is to come up with a model to think about computing not as a data center or an edge, but as a continuum that I can use in an effective way, right? And so that's really what I was trying to propose here, to start changing the way we think about computing rather than as silos, but as a continuum. And when we program middleware, when we program algorithms, when we program applications, we think of them to run across the spectrum with the right trade-offs, right? And so how do we do that? And we provided some research, but there are clearly many, many challenges. And here is just some of them, right? How do we drive computation through data, right? Where my workflow depends on the data I'm seeing, and rather than the other way around, right? So I express application behaviors in terms of certain characteristics of data, maybe the availability of data, maybe the content of the data, maybe second order statistics of the data, the average change of some characteristic, right? How do I define my workflow in terms of what that content of the data is? How do I accommodate the uncertainties in the data and the computation, right? How do I do something when I don't know that the data is going to be there or not, or the compute is not going to be there? Can I have the right trade-offs in there that says if I don't have the data, I can make this decision, but my error or my uncertainty increases, right? So how do I build that into the platform? How do I build applications where the workflow adapt to increase value, right? And this is interesting in the sense that, yes, I have a lot of data, right? But if I define my value in terms of timeliness, right, incorporating all the data is not the right option for me, right? So I need to, based on the resources I have or the time I have or the energy I have to make a decision that improves my notion of utility or value rather than defining static adaptations, right? So how do I make those trade-offs that says, yes, I found this new sensor, it has great data, but I don't have the resources. So I'm not going to incorporate it, right? I'd rather use this other one because now I can make my decision in a timely manner. So how do I define that value, and how do I adapt my workflows to continuously adapt and increase value? And the same thing with the execution, right? And then how do you build in models of trust and models of market models and things like that into such computations, right? Again, these are just some challenges I want to throw up. With that, let me conclude and take your questions. I hope this was interesting, and I'd love to get your thoughts in addition to your questions, whether this makes sense, and is that something we should explore as a community. Thank you for your attention.
Thanks, Manish, for this great overview. And we have now time for questions. But I think I will ask myself the first question because I was inspired by your challenges. It's a lot about data, just data, and we are kind of proud of collecting data, billions of data every day, zillions. DK has the exact numbers here, how much we generate. But the question, how much of this data is really useful? Is everything that we are generating, worth analyzing, worth running AI on top? Or there is something called dark data, data we should not even look at. We should just trash it because it's dangerous. So I don't know, in our community, I never heard this buzzword, but is there in our case a dark side of the data we should be aware of?
Absolutely, right? I mean, there's a lot of data that is not meaningful. For example, either its quality, timeliness, right? Yes, there's a lot of data, but if I cannot use it at the time when I need it, yes, eventually you hope somebody would go back and analyze it, but it's usually never done, right? And there's a concept I heard recently, which I did not know about. It's called worn data. I don't know if anybody has heard the term worn data. written once, read never. So, but the idea is the same, right? I think there's a lot of data, and that's why you need places where I can decide in an automated fashion, is there something useful that can help the task at hand, right? Now our model is, I never know when I'm going to use the data, so let me collect all of it and store it, right? Because I may need it tomorrow, right? And that often never happens. So the idea is, can I, be able to quickly, be able to, and then yes, I have to throw some data away because eventually that's what we have to do.
Okay. Yeah, when you talk about the reserve, usually you get this the gas reserve you keep there, never use. But when you talk about the computing resource reserve, you have a brand new computer that keep there, never use until you really need that, or you just keep some confusion. The people still use that, but when you need that, you can collect that. So no. The national can collect that, use them together.
It's like, you can think about the marine reserve, shipping reserve, right? It's normally used for every day, but when there's a need, you reprovision it and use it for the emergency. Right? So yes, it's there.
But then you have a national. This is really national resource. It's not a private resource, so you can.
It could be private, right? A lot of for example, the strategic marine reserve is private shipping, right? And so that's the model. Again, what we did was, is that it was what the committee did was they opened it up to everybody, and they got ideas from the community. And based on that, the blueprint is based on the responses they got from the community, from industry, from researchers, as to what is the idea here, how to build it. And some of the models are what you're talking about, right? You have a trigger, it's normal operation. You have a trigger, you go into emergency mode where it's used as a collective resource in this urgent way. And then you have normal operation again when the emergency is over, right? And how do you do that? And then the other thing, how's the platform that allows me to make that switch and be able to do these provisioning and allocations in this urgent way? What does that mean?
Yeah, so you need some Congress to get some law so you can use their resource, something like that, right?
You need, software stacks and application deployment stacks. So it's a very challenging, but I think it's also the experiences and technologies exist that we could do this, right? It just needs to align a lot of things.
I hope we get more questions. Yes, Masio.
Thank you, Radu. Thank you, Manish. It's a really brilliant. As Radu said, it's a brilliant. You can think. I want to link with your last consideration, where I see really challenge, because I was looking to the match rules and so on and so forth, and I look into the cameras. It's interesting to the fact that you don't need to count cars, but you need to understand how many cars are moving. In Messina, we're trying to understand, to collect many of events from different cameras, try to make some policy at the edge. Mm-hmm. I don't know if you have made some experience on that. So if you can really distribute not only computation, not only the storage, but is also this kind of processing events at the edge. Do you have some experience on that?
So one of the applications as part of this that Daniel has deployed is actually doing what you're saying, right? He's interested in what is the average number of cars that pass through a certain intersection, right, in a certain period of time. And then he needs to be triggered when that average number is greater than something, right? And so using on the Sage platform, he's able to do that, right? And so that's one. There was Another one he deployed, which is still different, is where they are looking at the air quality and the change in air quality. And if the rate of change is higher than something, right, because this area is impacted by wildfire and smoke, right, and they want to issue a warning saying that if change is you have to quickly let people know. And so that's another one where we are measuring the rate of change across a whole set of sensors and be able to trigger not on the value of the sensor, but on this, and you do that at the edge.
Last time for questions before the coffee break. So let's go for a coffee in the sun outside. Okay. Oh, yes, we have to. First of all, thanks, Manish, again.
Thank you very much. Thank you, Radu. Thank you very much for your presentation. And I mean, congratulations and thank you very much.
Thank you very much.
Okay. A picture for the press, but Radu, please.
So a small announcement, there are many, I don't know why they are printed, but many certificates of attendance you can get on the desk just to bring with you. I know it's not good to print stuff, but they want to print, please take them, okay? You can put in your wall, in your office. Please take the certificate, okay? Okay, we start again at 4:30 for, let's say, we'll have a break now, and then a session we start 4:30, okay? Thank you.
Jayu Wang, can you hear me? I enabled your mic and camera.
Okay.
Okay, I see you.
I can hear. Right.
Okay.
Can you hear me?
Yeah, I can hear you. Just a moment that we configure the Teams.
Okay.
Okay, start to share the screen. I present you in the meantime.
Can I start?
Can you share the screen?
Share the screen. Okay, I click. Okay, can you see?
Okay, I see it. So in the meantime, you can also have full screen. So the first presentation in this session, Future Internet and Computing Systems, is by Jayu Wang. The paper is titled A Distributed Vehicle Assisted Computation Offloading Scheme Based on DRL in Vehicular Networks. So please, Jayu, go ahead. Stage is yours.
Okay. Thank you, Mr. Chairman, for your introduction. Dear friends, my name is Wang Jiayue. I come from the School of Electronic and Information Engineering, Beihang University, Beijing, China. I'm honored to have the chance to share our research on this special occasion. The topic of my paper is a distributed vehicle assistant computation offloading scheme based on deep reinforcement learning in vehicle networks. The outline of my talk as follows. The first part, I want to introduce the background of this research and our contributions. Second part, introduce the system model and our proposed algorithm. Then the simulation experiment and the result analyzed. Finally, a conclusion is given. Okay, the first part. The motivation of this work like this. Recently, with the development of 5G and the Internet of Things, the explosion growth of new mobile applications has led to an increasing number of computation-intensive and latency-sensitive tasks, such as automatic drive and augmented reality. These tasks result in high resource consumption of mobile devices, especially for resource-limited vehicles. Mobile edge computing is recognized as an encouraging paradigm. It can break down the service from closed center to the edge of wireless access network. Computation offloading is the key technology in MEC that determines which tasks should be offloaded for achieving the minimal time and energy consumption. Next, I want to summarize some previous work experience in this field. First, previous study only considered fixed MEC server, but it can't meet dynamic demands of high-speed moving vehicles. So we consider using the vehicle as a mobile MEC server. Second, current work primarily focuses on binary offloading and simple particle offloading. But in practice, the dependence between tasks can't be ignored. We use direct acyclic graph to represent it and design a scheduling mode based on the priority of computation. Third, previous computation offloading methods such as game theory and intelligent optimization algorithms are not sufficient for high dynamic scenario. Thankfully, in recent years, deep reinforcement learning has huge development. It can interact with the environment to obtain an optimal policy and maximize long-term gains. Finally, some study has used centralized control. It requires collection of all information about the users, but users may refuse to disclose that for previous reasons. Distributed control benefit previous requirements. Let's move on the second part, system model and algorithm. The framework is shown in the picture. There are different vehicles randomly distributed on a highway. Some are mission vehicles and some are service vehicles. The roadside unions uniform distribute along the roadside. They connect with the baseline with favor. Tasks generated by vehicle can be executed locally or offloaded to a fixed MSC server or a mobile MSC server. V2I communication use long-term evolution or 5G. Communication between vehicles use dedicated short-range communication, DSRC. Each vehicle can generate the application-level tasks with DAG structure. We use some eligible vehicles with idle computing resource as vehicular MSC server. Each car has a task schedule that decides where the task should be performed. A task can be divided into a number of dependent subtasks. As displayed in picture, a circle represents a subtask and a direct edge indicates a dependence. The number on the edge represents the amount of data for this task. According to the processing time of the subtask, the priority of all tasks is calculated from the exit task forward. Then we can sort the task by priority to get the scheduling order. Then the communication model. In the case of local computing, time and energy is determined by local processing power. In the case of offload, in the case of MSC computing, the delay is the transmission time plus the processing time and the return time. The energy consumption consists of data transfer energy and maintenance energy in the idle state. With the above description, the offloading program we can form is minimize the weighted sum of latency and energy consumption for all applications in system. Next, we present a DRL-based offloading scheme to solve the problem. First, for distributed systems, each vehicle has an agent whose elements are shown below. Data space is consisted of 4 parts. S1 is DAG task structure information of the vehicle. S2 is current radio bandwidth of each MSC server. S3 is the offloading decision of other vehicles in previous time slots. S4 is the current candidate service vehicle metric. The action space is an offloading decision for each vehicle. The reward function is the degree of performance improvement of the current action. Okay, the picture illustrates the DRL-based multi-agent vehicular edge computing offloading scheme. Each vehicle agent has a set of actor network and a critic network. By interacting with the environment, the actor network outputs the action. The critic network obtains the value of that action. Then we put the transition into the replay buffer. When the buffer is full, simple small batch, mid-batch date to train the actor network and the critic network, and then update the parameters. Finally, calculate the average reward for each agent. We maximize the long-term expectation reward based on policy gradient. Okay, to evaluate convergence, we use PPO algorithm for training. The training object with policy can be defined by this formula. On the right is a pseudocode of the algorithm. I have introduced it in the last page. So let's move to the experiments. We have done some simulation experiments to verify the effectiveness of present algorithm. Some simulation parameter setting are shown here. Vehicle speed are regionally distributed from between 20 meters per second and 30 meters per second. Vehicles and MEC server are set with different computing capability. V2I and V2V communication have different bandwidths. First, the convergence is first considered. We compare our algorithm with some benchmark method. First, D-AC means without vehicular MEC server. FC-AC means only have fully connected layers in network structure. D-DQN means it's based on deep Q learning. Rhythm means the agent rhythm selects the location of the task to be performed. From the picture, the horizontal axis is episode. The vertical axis is a system utility. It is a normalized reward. Our purpose, the algorithm achieves the best system utility and the fastest convergence rate. Compared with D-AC, it can prove the importance of vehicle assistant computation offloading. Compared with the FC-AC, it proves the optimized structure helps to extract key information effectively. Compared with D-DQN, proves the actor-critic algorithm has some superiority over DQN. Then we compare the performance of proposed algorithm under different learning rate of the actor network and the critic network, and we get the best combination. The critic learning rate is gradually larger than actor learning rate. We then explore the influence of different numbers of vehicles on performance. In experiment, we changed the number of vehicles from 10 to 30 in intervals of 5. First of all, our proposed algorithm achieves the least time and energy cost. For latence, algorithm with vehicle assistant show a process of decreasing and increasing. The reason for this is that as the number of vehicles increase, more vehicles are served as mobile MEC server and more computation resources are available, resulting a decrease in overall latency. But as the amount of vehicles continue to rise, the load on both fixed MEC and mobile MEC increase and the overall latency rise. In terms of energy consumption, the number of tasks to be proposed increase as the amount of vehicles rise, so the overall energy consumption gradually rise. Finally, we compare the different performance for latency and energy consumption in utility function. We can see different algorithm has disparate performance for latency and energy consumption, resulting variability in long-term average reward. Finally, a brief summary. In conclusion, this paper studied the computational offloading problem in vehicle networks. We utilize vehicles with spare resource as mobile MEC servers and propose a distributed deep reinforcement learning based algorithm. We consider the dependence aware task and previous prevision, optimize the network structure of actor-critic algorithm, use convolution neural networks to extract rich state information. Experimental results reveal that the proposed scheme has a performance improvement compared with benchmark algorithms. In our future work, we will consider the resource processing problem of MEC and combine deep reinforcement learning and Stocker-Burger game theory to make more reasonable calculation of loading. That's all. Thanks.
Thank you, Jayu. So this is time for questions. Okay, I have a question for you. So I would like to know how you designed the actions of your reinforcement learning algorithm. I mean, how do you select the vehicle's target where to make the offloading? Is a random vehicle in the graph? Is a next hop with the minimum weight? Is something else?
How to start the algorithm?
And talking about the action of the algorithm.
Action of algorithm. Yeah. I think about it.
What is the vehicle where you do the offloading? So I'm the vehicle and then I move my computation to the next vehicle with the action of your algorithm. I mean, is the next in the graph I image?
Next, we use the sorry, Sorry, I understand that a bit
It's okay, Joe. It's okay.
difficult.
It's okay. Some other question from the audience? Okay.
Thanks for the presentation. I was just wondering how you, if you could go over again, how you quantified the energy consumption on the vehicle for offloading the computation.
How to? Can you speak slower?
Sure, sorry.
Thank you.
Could you go over the energy consumption calculation again?
Accurate the in the training by这个 PPO algorithm is based on actor critic. When update the policy, we constrain the next policy and last policy. They restrict the distance between two policies.
Okay, thank you.
Okay, thank you.
Thank you, Jayu. Thank you for your presentation. Okay, now I invite Alexandra Obeso-Duque to take the stage. Please add and prepare the presentation.
Okay, thank you.
Okay, hello everyone. My name is Alexandra. I work at Ericsson Research Area Cloud Systems and Platforms, and I'm also an industrial PhD student at Umeå University, Sweden. This work has been done in collaboration with my supervisors, Christian Klein, Eric Enroth, and Björn Skubik, and also my colleagues, Jim Feng and Shushun Kai. And yeah, so at Ericsson, we are quite interested in building the future mobile edge cloud platform in which we can offer strong quality of services for emerging applications such as industrial use cases and enterprise use cases. So yeah, so let's talk a bit about service mesh. Sorry. So why are we doing this? Well, as many of us know, technology needs to be evolving quite fast to be able to cope with the ever increasing performance demand of applications of new use cases such as automotive, smart manufacturing, immersive experiences. And the cloud has also getting more and more distributed and decentralized. And here we are focusing on when we have resource constrained data centers deployed in close proximity to radio access networks. And on top of that, we want to host third-party applications that are based on microservice-based architectures in which applications can be composed by hundreds or even thousands smaller components. So yeah, there are good opportunities to enhance performance with mobile edge cloud, but at the cost of an increased complexity of the system. Application developers and operators are getting quite overwhelmed with the work, with how complex it is taking care of management of applications in an optimized way. In particular, how to handle service-to-service communication, and different tasks related to traffic management, where service meshes have been an alternative approach for traditional ICT use cases. So what did we do? So we wanted to see how this existing service mesh design would fit to address the performance requirements demands related to traffic management of mobile edge cloud workloads. And the way we address this problem is by collecting the characteristics requirements of mobile edge cloud and their workloads. And we call them our evaluation criteria. And then we studied the state-of-the-art design of the service mesh, functional, non-functional characteristics, design drivers of service mesh. And then we contrasted the two of them in what we call our qualitative evaluation. And from this result and our main contributions to the research community are the identifications of strengths, limitations, and trade-offs of service mesh, comparing traditional use cases versus emerging use cases, and rather new research opportunities in the area towards mobile edge cloud specialized service mesh. So what did we learn from this work? We learned that today's dependability-centric design of service mesh is really targeting reliability, availability, and scalability, so on requirements of traditional use cases. However, many of the features of service mesh either fall short or become limitations when addressing performance demanding workloads. So it's not a surprise, but service mesh is not suitable for mobile edge cloud workloads today. So the trade-offs, we see different trade-offs in terms of usability. Later, I will explain a bit more about that. So the level of usability towards application developers and operators versus the implicated performance cost of the underlying mechanisms service mesh relies on. And we do see the need of having service mesh and cloud native, cloud platform abstractions, but we need to tailor-make the design of service mesh to actually target requirements of mobile edge cloud workloads. How many of you know about mobile edge cloud? I guess you have heard many talks about it by now, right? And what about how many of you know about service mesh? Okay, so let's get all on the same page. Well, I won't spend so much time about mobile edge cloud. I talked about that a bit before as well. For the sake of time, we know that that mobile edge cloud is trying to offer support for offloading of the complex execution tasks that cannot be computed in resource-constrained devices. From the 5G, 6G use cases, we can we can see that there are different type of application demands. We have latency sensitive applications, bandwidth demanding applications, mission critical applications, and I think they are self-explanatory. So we want to have real-time responsiveness of end-to-end responsiveness of the system. We want to support high volume of transfer of data, and we also want to support or give support for the applications that cannot tolerate downtimes in the system. So the good about the mobile edge cloud is that by placing the data centers closest to the end user, then we get lower transport delays. We also get we can also avoid congestion in centralized locations of the distributed cloud. We can provide broad coverage of the network and geographic redundancy. However, the bad side is that this is a really complex system of systems that entails multiple technology domains, distributed cloud, mobile networks, which are complex, and then the application, the architecture of applications, modern applications. And then we cannot only host cloud native network functions, but we also want to host third-party applications, such as the ones we have talked about, that have diverse requirements, and then therefore may have also different characteristics of the traffic and support, of course, the ultra high performance demands of these applications. The challenges that we encounter in general is that we need to address the design of the system in a holistic way. It is not enough to just set some data centers close to the access networks and that's it. You won't really get the performance gains by doing that, because we need to have close integration between the mobile network and the edge cloud. We need to have close coordination, alignment of the mechanisms that the different technology domains employ to have an efficient architecture. We need to have also support for different ways of ensuring QoS in a way that we are aware of the different performance demands, and then the system should have higher levels of autonomy, because I mean, a human operator won't be able to manage these complex systems in a timely manner. So now, what is service mesh? Let's say before service mesh, we had a distributed set of decoupled microservices, and then application developers needed to take care of not only the application logic, but then encoding traffic management logic, such as traffic control observability, into the application logic. And when we have polyglot applications, then developers needed to spend redundant time doing the same task in different languages. So the service mesh has come to alleviate some of these difficulties. So the service mesh proposes that the coupling of the traffic management logic into a data plane and control plane. In the data plane, we have a set of architectural connectors, proxies, and gateways that are enforcing traffic policies. And then the control plane, in a simple way, is performing propagation of updates in the traffic policies towards the data plane. And then on top of that, we need to have a way to manage the service mesh with federation, interoperability, lifecycle management as well. So a brief history of service mesh. In 2016, we see the appearance of service mesh, the first service mesh implementation, Linkerd, that service mesh have been driven a lot by the open source community. So here are some examples of that. We have Istio, which is today one of the more mature featureful implementations of service mesh, and which is well adopted. And today we have more than 20 implementations of service mesh. And we also have discussions about going proxy or proxyless, we're using proxy or proxyless approach for the data plane of the service mesh with disrupting technologies such as eBPF to enhance the performance of the data plane. Then in the research community, there has been a bit more, much more scarce interest, I would say. We have in 2017 Stanford University working on a proxyless approach for service mesh called AppSwitch. Then we have interest from the telco community, some of them from Ericsson, studying state of the art and general future research opportunities in the area, and also comparing software-defined networks and service mesh, and then proposing merging the two of them. And then from Umeå University, we also have good works towards self-adaptability of service mesh, in particular adaptive circuit breaking response caching logic. And also there was from University of Fortaleza and Carnegie Mellon. So let's come back to the lessons learned. And let's break that down. So previously, I was mentioning that about the dependability-centric design of service mesh. Why am I talking about that? Well, we collected the functional characteristics of service mesh, and we realized that in the conditions of control, actuation mechanisms, and observability mechanisms, many of the building blocks are targeting availability, reliability requirements. So circuit breaking, traffic mirroring, outlier detection, etc. And then we have also that on top of this, you can build up more elaborated use cases supporting CI/CD pipelines, and zero downtime rolling updates with canary deployments and so on. And then in the non-functional or architectural design of service mesh, we also have that the sidecar proxy pattern, and which is good in a way because then you can isolate faults across this mesh of microservices and reduce the blast radius in case of failures. But then if we analyze this versus the requirements of emerging use cases, we see that this set of features for dependability-centric design constitute a basic set of features for mission-critical applications. However, in terms of bandwidth-demanding applications, we see few features such as rate limiting, traffic splitting, which could help there as well. However, there is not much considerations regarding how to support latency-sensitive applications in a way that you can manage the traffic in such a way that we can ensure real-time responsiveness in long chains of microservices. And also the architectural design patterns that underlie service mesh, many of them have serious performance and resource overhead. And not everything is bad, I forgot to mention. We can, in terms of mobility support in Mobile Edge Cloud, we can really exploit zero downtime rolling updates if we want to have, for example, application migration across edge clusters. We have experimented a bit there, and it's very nice to see how this can be used for something more elaborated. Then in terms of flexible control and observability, we can say that, yeah, in service mesh, you can configure traffic based on policies, right? And then you can specify those policies in a way that you are aware of the deployment models you use for your application. So you can manage traffic based on information about clusters, namespace, nodes, services, subset of services, and even endpoints. So anything that can be encoded in the pod as a label or an annotation. Yes, and then in terms of deep request inspection, you can also configure policies based on methods, URIs, HTTP query params, headers, information that is encapsulated in the header of the requests, and so on. So we have layer 4, layer 7 awareness, which is something different to SDNs. And then if we look into non-functional, into observability, observability characteristics, then we have the features such as distributed request tracing, in which could be exploited for root cause analysis of failures as well, with very fine granularity. However, yeah, having flexible control and observability is in a way based on the sidecar proxy pattern, which has been broadly discussed, yeah, about the limitations of it. Having, for example, in Istio, in the case of Istio, 2.7 milliseconds overhead per pair of sidecar proxies. And then we have the cases for deep request inspections, which may also, in some cases, cause overhead and bottlenecks. And we also have that maybe not all the different type of applications will require the same granularity in terms of control and observability. So how often are we collecting data? Maybe a bit related to the previous talk. Are we really going to use that data? So, and the overhead that is caused by collecting that data as well, which is not always needed. So we have here the first trade-off, so in which related to the usability, so the level of flexibility in which application operators can configure traffic policies versus the implicated performance cost. Then we have that service mesh, more than just an architectural pattern for connectors, really offers platform level abstractions for traffic management, for simplifying traffic management. And yeah, this is an older version of the slides. But yeah, having the couplement between the logic, the traffic management logic in management control and data plane really addresses concerns of DevOps practices and is trying to centralize, unify, and make the logic consistent as well, which is good in a way for traditional use cases and even for emerging use cases. However, if we consider, for example, the case where, for example, a bandwidth demanding applications, we can have bursty load. And if we can imagine that service mesh has some sort of intelligence that can adapt policies across the different components in the data plane in an on-the-fly manner, then we can see that there could be several bottlenecks for propagating policies at such high frequency, and which can also cause certain overhead and congestion in the network, which is actually shared also with the data plane. And then we have that also that these proxies still relied on the well-known match and well-used match action abstraction. And I think it's time to reevaluate that and see if having more intelligent connectors, architectural connectors, then is this the right approach still? Yeah, I won't talk about technology fragmentation due to time, but then here we have a trade-off between the level of complexity abstractions that service mesh provides versus the incurred performance and bottlenecks overheads. So to conclude, we have that, yes, service mesh is good for traditional use cases. It really has fine granularity in the control of policies, the coupling of concerns, and so on, what we already discussed. But yeah, it is today, unfortunately, unsuitable for emerging use cases due to the performance overhead, because there is no awareness of the different type of requirements of future use cases, and is still very oriented to human operation, human-based operation, which won't really be the case in mobile edge cloud. Then we have the different trade-offs that we talked about in terms of usability versus performance cost. And looking forward, we do see the need of service mesh again. We really want to encourage research in the area because we need it. We need to, it's not just enough to reduce the latency in the mobile access networks. We also need a cloud stack that is performant, including also levels of abstraction for operators of the system. So here we have several areas in which we could continue doing research. And yeah, looking forward, we want to complement this qualitative evaluation with a quantitative and experimental evaluation of service mesh. Thank you. If you are interested, please go here. You will find much more information than in this talk. And feel free to reach out if you have any questions.
Thank you, Alexandra. Any questions?
Yeah, thank you for the presentation. Yeah, it was very interesting. I am also very interested in this service mesh, and I'm going to use it for my next project. I'm just interested to know a bit more about the limitations of this service mesh. Like, I have a few questions, but I think we don't have that much time. I just wanted to ask one question. Like, service mesh is on top of Kubernetes, basically, if I understood properly. And in use cases of like edge computing and also mobile edge computing, that we have very resource limited devices that sometimes are not able to run Kubernetes and things like that. If we want to just have the benefit of service mesh without having Kubernetes and actually this service mesh, what's the essence of this service mesh that we can just take it and use it in another system with like a particular design, so we can just benefit this service mesh? Like, do you have any idea of what's the essence of this service mesh?
Yes. Okay. Yes, I mean, as you see here, we were still not looking into like fog computing in like really constrained devices. We still, have constrained data centers, but not to the level of, for example, IoT devices. However, we do see that in the future, we would like to look into, for example, how to provide osmotic computing all the way to the more constrained devices. And I would say that the essence of service mesh is really how you have these unified architectural connectors that are consistent and that allows you to have really fast adoption from application developers and operators, because we really want to bring out the value of Edge Cloud as soon as possible. And like having this really complex system of systems with such performance demands, it's going to be hard for the new emerging use cases and application developers and operators to really adopt and change like their ways of working and like understanding the complexities of the system. So the service mesh, the essence of the service mesh is really providing these platform level abstractions of the underlying complexities in a way that you can have traffic management in a consistent way. Yeah.
More questions? What are the next steps that you will get now?
Yeah, the next steps are, we are actually now looking into, I mean, this was very conceptual analysis, right, of service mesh design from a like software design perspective as well. But yeah, we want to complement this with a quantitative evaluation. We actually want to quantify how much are the performance overhead of different implementations of service mesh and different options in the underlying architectural design patterns of service mesh. So yeah, we want to understand the quantification of these trade-offs between the value of service mesh and the cost of having a service mesh.
Thank you, Alessandra. Okay, this is time for next presentation. So Kevin Asogba, I guess he's online. Let's check it. So the paper is titled on realizing efficient deep learning using serverless computing. Kevin, can you hear us?
Yes, I can hear you. Good morning.
Okay. Please share the screen.
Can you see my screen now?
Yeah, we can. Go ahead.
Okay. Hi, everyone. My name is Kevin Asogba. I'm a PhD student at Rochester Institute of Technology in New York. I'm honored to present our collaborative research with Virginia Tech today, which focuses on realizing efficient deep learning using serverless computing, more precisely functions as a service. In recent years, we've noticed an increase in the number of cloud applications developed and deployed using function as a service paradigm, mainly due to the cost model which it provides, but also due to the ease of use of fast platforms. Serverless computing doesn't require any system update from the user, and also by abstracting server management from an end user, it provides ease of use and is affordable for every type of user, irrespective of their background. However, there are some constraints which come with the use of fast platforms, mainly the isolation of running functions, which prevent two running functions from communicating. Also, there are some restrictions in terms of resource utilizations, where fast platforms have restrictions on the amount of memory to allocate to a running function, but also on the timeout of their execution. Despite the cost and resource efficiency that fast platforms offer, we also observe that these restrictions and isolation of functions are challenging to the deployment of many cloud applications using fast platforms. To demonstrate those impact and the limitations, we consider a case study of a cloud inference provider, which has a pre-trained model staying in an external storage and used for inference services in the cloud. In order to maintain that model accurate, the company uses the FAST platform to periodically retrain the model and improve its accuracy and also incorporate the latest data. Using that case study, we used the MNIST data set to train a convolutional neural network using a batch size of 64 over 5 epochs, feeding it into Apache OpenWhisk, which is an open source serverless platform, and using the default memory and timeout allocations of Apache OpenWhisk, we observed that the execution failed due to the lack of memory resources. We noticed that because increasing the memory allocation up to a certain threshold allowed the successful execution of the same workload of the same job. These are challenging because as an end user, you will know the appropriate memory and timeout to allocate to a running function prior to its execution. It is also challenging as resource utilization in the cloud is an important matter in distributed systems and needs to be addressed carefully. And providing a high quality of service to the user, we wouldn't like the user to execute a job which will always fail. The importance of a function as a service nowadays for deep learning is more emphasized because we have millions of parameters involved in the computation as well as thousands of tensor operations. On traditional platforms, including CPUs and GPUs, there are some limitations which can be summarized as the limited level of parallelism on the CPU and the high expense that comes with provisioning a GPU in a cloud platform. However, using a fast services, function as a service, we have the ability to deploy thousands of concurrent functions and all that at a low cost. It enables the execution and the deployment of diverse types of applications, which in our case, deep learning is the target. Our goal is to not only determine the appropriate memory and timeout limitations of the running serverless functions, but would also like to improve the data center resource utilizations by carefully orchestrating the execution of the serverless functions. We also intend to improve the performance of the DL workload by reducing its execution times using different optimizations. For that, we propose DSDL, which is a distributed serverless deep learning framework that helps us in achieving those objectives. DSDL targets the limitations of the fast platforms by redesigning the deep learning applications at the granular level. We employ a fine-grained design, which is achieved by using a batch splitting approach that helps us control the workload of each function by executing different chunks of by training the model on the different chunks of the data in different functions. This is helps us to ensure that the workload in each function is reduced. But if you could notice from the figure, the model that is trained in each of the function remains the same. Now that shows that in our approach currently, we just use batch splitting to control the workload. And as multiple functions are executed, we needed a way to orchestrate the application execution where we used a controller which not only launches the training functions, but also executes an aggregation function which takes the models trained by each of the training function to reproduce an ensemble model by running a weighted aggregate. The execution is dependent on the number of functions that the workload is composed of, as this number has an impact on the success of the workload. We correlate the estimated memory with the maximum function that is allowed on the serverless platform to be allocated to a running function. And after our estimation, we check whether our estimate is higher or lower than the maximum memory, and dynamically readjust the number of functions that workload will require to successfully execute. Memory estimation is a key part of our design, and the determining the memory that is to be allocated to a running function is dependent upon the dimensions of the input data, the batch size, the structure of the model, and also has to take into account the maximum action memory. To estimate the memory for a running function, we consider the size of the Docker image that is used to build the Docker runtime, the serverless runtime. We also include the size of the data set that is being trained on. We add it to the size of the model. We compute the size of the model considering the dimensions of the model structure, the features, and the kernel size. We add that to the memory utilization during the training process itself. And we also reserve some safety limit to account for cases of memory leaks that may occur during the training. Our memory, to compute the memory of the training process itself, we added the memory utilization of the parameters, memory utilization of the activations, and the miscellaneous variables. The total number of the parameters and the total number of activations are computed considering all the features of the model, the kernel size, the filters, and other model-specific features. We also multiply them by the number of bytes used to store each of the variables in order to obtain the memory utilization in bytes. In most cases, that factor is equal to 4, as most deep learning framework use a 32-bit precision to store their variables. Additional information about how we compute the total number of parameters or how we compute the number of activations are provided in our paper. To get the timeouts that should be allocated to a function, we consider the expected cost of the user, the number of containers that we deployed, and our previously estimated memory. We also have to take into account the unit costs that the serverless platforms has defined for any serverless function. This is often dependent on the time that the execution has taken, and also the memory reservation or memory utilization of the workload. We have aggregation services which take the model from each of the container and runs a weighted addition of those intermediate weights to obtain an assembled model. I'm going to explain deeper the entire workflow in the next slides, but for further information, you can always refer to the paper. End-to-end workflow of this style starts from the controller that takes the user inputs, the user's request, and next it launches different functions to execute the workload. After, based on the number of required functions, we have a number of chunks of the data that is retrieved from an external storage and used to train the same model in all cases. As I said earlier, we're using batch splitting in our paper. And by doing so, we have different sets of weights that is obtained from different model training processes. Each of those intermediate weights are stored in an in-memory data store after training is completed. Once the training is complete, we have our controller launch the aggregation service, where the aggregation container adds up the intermediate weights from each of those models to obtain an assembled model. And that assembled model is stored back into Redis in our case, but we also allow the user to define where that model could be stored. In some cases, some cloud providers may want to store it in an S3 bucket if their inference services take the model from that S3 bucket. I'd like to draw your attention on this design in another way. As we're using batch splitting in the design of this DAO, it can also be extended to having to incorporate model parallelism where the model can also be shared across multiple functions to run the execution. That design can also be included into DISTA, and we intend to explore that in the future. We evaluated the design of DISTA on the Chameleon testbed and used Apache OpenWhisk as our serverless platform. We considered 4 different deep learning models, which are Inception V3, ResNet 50, ResNet 152, and VGG model. The datasets that we selected are MNIST, SAFR10, and DMLab. Those datasets have been selected in that way because we wanted to explore the size of the data and their impact on the model training to see how would this data perform as the size of the dataset grows. We have 2 baselines that are used to evaluate the performance of this data. The first being the default serverless TensorFlow that illustrates the deployment of a TensorFlow code on the Apache OpenWhisk platform. In this case, we assume the user has already knows the variables, the configurations of those containers prior to the execution. In other words, we assume here that the memory and the timeout needed to execute that job are already known. So we didn't have to run any experiments by trial and errors in order to determine those values. This brings us to declare that this environment is an ideal serverless environment, as in a normal settings, there should be multiple retries until that value, the appropriate configuration is determined. The second baseline is a bare metal TensorFlow that simulates the deployment of the deep learning workload directly on the virtual machine. This is the best case scenario, as it doesn't have any additional layer of virtualization and has the ability to use all available resources on the machines. First, we compared the memory footprints of each of the execution environments, and we observed that although DISTA has a higher memory utilization in total, we have a better system resource utilization. First of all, we're using multiple containers to orchestrate the execution of the workload, giving us less memory per container. And with less memory per container, DISTA offers the platform the ability to host additional containers from other applications. The importance will be more emphasized in a batch when a batch job is executed where there are multiple applications. With this DEL, there can be other containers from a second application executing on the same platform. But with default serverless TensorFlow, having a single container executing the entire workload, it is challenging to launch a second application on the same platform if the memory that is available exceeds the memory that is needed to run the entire workload inside one single container. Therefore, we have a better system utilization compared to the default serverless TensorFlow. Comparing the execution time, we observed that DISTA yields a better performance as we reduce the training time by 46% and 40% compared to default serverless and bare metal, respectively. This is due to the reduced workload that we have in each of the containers, the ability to launch multiple containers to orchestrate the execution. It is also important to notice that the aggregation services didn't have a significant overhead on the execution, giving us an edge over bare metal TensorFlow and default serverless TensorFlow. For instance, in a case where we train the MNIST dataset, which has 60,000 data points, if we launch 2 containers with this, each of the containers is it's training the model using 30,000 record of data. So with a reduced data sets in each of the container, we have the ability of while running the workload in parallel to complete faster than what this default serverless TensorFlow or bare metal will take to execute the 60,000 data records. So that gives us the ability to reduce the total execution time. Knowing that we are running functions in different containers and running them on the serverless platform, it is important to observe the impact on the training accuracy, as that is the most important for a cloud provider or an inference service provider. We observe that when we consider Cypher10 data sets with all the models, Distal obtains a higher accuracy than default serverless and bare metal TensorFlow. However, with smaller data sets such as MNIST, we have a slightly lower accuracy than bare metal and TensorFlow. These are due to we hypothesize that these are due to the size of the data sets, and also the fact that when we have multiple containers training with Cypher10, each of the container has more data to train the same model on. Whereas in the case of MNIST, we only have a lower number of data points to train the same model on. That is why when we compare ResNet 50 with both MNIST and Cypher10 dataset, we observe that each container with MNIST had less data than what Cypher10 was offering per container, giving Distal a higher accuracy per container. And therefore, after running the aggregation services and obtaining the ensemble model, we were able to get a better accuracy in general. As we have a top tier accuracy of up to 98.7%, which is production level accuracy, we say that this can be deployed in the production level and can provide higher efficiency at inferencing, at conducting deep learning inference services. Finally, we evaluated the impact on the cluster size. As we grow the number of nodes in a specific cluster, we wanted to observe if this scales better, and our results confirm that we scale better compared to the other baselines, as the performance gap between bare metal and us decreases as the number of nodes increases. We also observed that compared to default serverless, we have a higher reduction factor than the default serverless TensorFlow, as we reduce by 0.4 times, whereas default only reduces by 0.27 times. So not only are we scaling better than default serverless, but by reducing the gap compared to bare metal, we also scale better than it. The reduction of the gap between bare metal and Distal is also due to the fact that with bare metal, all the nodes are communicating between each other, and then there is an additional overhead that is incurred due to communication, and there are other cases of contentions that may happen as the number of nodes in the cluster grow. In conclusion, we propose a system that provides efficiency in running deep learning workload on serverless platform. We determine the appropriate memory and timeout resources to allocate to each of the functions that compose the DL job. And we integrate it with Apache OpenWhisk to demonstrate its practical use. Our evaluation and conclusion confirm that we not only reduce failure, eliminate failure, but we also reduce the consumption of the memory per container while reducing the training time and maintaining a high accuracy. In the future, we would like to explore hybrid parallelism to avoid failures that may occur due to the model size by combining both data and model parallelism. Currently, we're just running a batch split approach, which doesn't account for cases where the model size outgrows the maximum memory that is defined by the serverless platform. We'd also like to explore hardware-based acceleration of serverless computing to explore whether GPU will give an edge to our execution and will allow us to complete the job faster than what we're getting by using just a CPU platform. Thank you very much for your attention, and I'll be happy to take any question you have.
Thank you, Kevin, for your presentation.
Thank you.
Any questions here in the room? Okay, Kevin, I have a question for you. So this is really an interesting approach to distribute the training, then reducing the training time, but maintaining the accuracy higher. I see that the aggregator also is an important part of this. So what is the policy of aggregation that you use?
Yeah. In this design, we're just adding them. We are not applying a weight on the models. A way to extend it will be to have a weighted aggregation, but we chose to just have the weight equal because the same model is being trained in each of the containers, and the same size of the data is distributed across. So we don't have an edge over. There is no container with higher priority than the other container, as they're all running the same workload, and the same size of the data. I mean, this design can also be used in cases of ensemble learning, where if different models are trained in different containers, then the weighted aggregation can be extended to be a weighted aggregation, actually with the higher weight for some of the models which the developer deems with a higher accuracy than the others.
Okay, more questions? Yeah.
Thank you, Kevin, for this interesting talk. I just have a question. You are improving the execution time and the memory consumption. I can see that execution time is improved because of having like parallel replicas of a function that are handling this task execution. But we are adding more containers for having more replicas to run the task in parallel. And the containers are consuming some memory, although the containers are having like very low memory footprint. Still, we are consuming some memory for just adding the containers. Do you think it would be an improvement if we consider vertical scaling of our functions? Sometimes, like if we are going to have 10 replicas for our function, instead we have 5 replicas to keep the parallelism, but at the same time, we increase the size of the containers in terms of memory. So we make a trade-off in here. So we don't consume a lot of memory for adding more containers. Do you think that would be an improvement?
Yes, thank you for the question. Vertical scaling, as you described it, will definitely be an improvement of the system. However, the number of containers that the approach Distel uses to compute the number of containers already considers the maximum memory that the serverless platform allows. So if we employ vertical scaling in this case, it means that by adding more memory resources to a single container, we might end up exceeding that maximum limit and therefore the container failing. That is why we not only are ensuring that the memory which we have is as close to the maximum as possible, but we have a number of multiple containers to run. And the reasons why we have a higher memory utilization in total here is because we have the same model in each of the container. And if the model size is higher, we are consuming a high amount of memory reserved for specifically holding that model. That is why we are planning to extend it to model parallelism in the future to explore whether we will gain some performance enhancements in that regard.
We have another question, Kevin.
Thank you. Good talk. I have a question because in the cloud serverless offerings, you are getting more CPU based on the memory you are allocating to the function. So in practice, if you are in Amazon Web Services using Lambda service, if you are reducing the amount of memory you are using, you're also being penalized because you're using less CPU. So I like your idea of reducing memory, but if you port your idea to the cloud using fast platforms, commercial fast platforms, you will have less CPU. So you will be impacted in the training time because you will increase it. You will manage better the memory, but you at the same time will be penalized because you will have less CPU available. So do you have any comment how to avoid this? Because
Thank you for the question. Absolutely. The way it is designed is that more CPU resources are allocated when the memory resource is larger. That is why in order to determine the number of containers to launch, we consider, after estimating the memory, we look if it is higher than the maximum memory. So the maximum memory normally would give us the maximum CPU resources as possible. So by starting from 2 containers, it is likely that after the first iteration, we hit a number either a little higher than the maximum or around that sphere. So we are still maintaining a higher memory allocation when we consider the maximum that the cloud provider enables. And therefore, we are kind of reserving as much CPU resources as possible.
Okay. Another question, because now in Amazon Lambda, you have available up to 10 gigabytes of memory that give you 6 virtual CPU cores. So you can run, I mean, internally, you can exploit intra-level parallelism within the same function. Have you thought about leveraging that kind of parallelism? Because you will have like, you have 6 cores, you have branching parallel, you can branch TensorFlow, you can train a neural network within the same function, you have 6 cores, and you can have multiple instances. Because it seems that you have like one container, one CPU core, or I don't know how you allocated the resources, because you are talking all the time with containers, but you are not telling the details. How many CPUs is using the container, or, I mean.
Thank you. The current implementation of Distal uses TensorFlow. And with TensorFlow, we're using the mirrored strategy to train the model inside a container. So the mirrored strategy being a distributed strategy, it already makes use of all the resources available within that same container.
Okay. Okay. So thank you.
Thank you. Thank you.
More questions? Maybe there is time for another question. Okay, so at that point, thank you again, Kevin, for your presentation.
Thank you.
So the session now is closed. So see you later at the social dinner that starts beginning at 20. Bye. Bye, Kevin.